morning. Last time I was talking about introduction to zeolites. We discussed the composition of the zeolite. It is said that zeolites are water containing crystalline aluminosilicates, right, depending upon the silica to aluminum or silicon to aluminum ratio, different kind of acidity or concentration of acid sites that can be obtained in zeolite material, right. So, this can be a synthetic natural zeolite also, clay materials, right, or it can be made from some structured materials, right, template using some templating agent organic materials. So, preparation I will talk later. The mainly zeolite consists of silicon SiO4, right, tetrahedra and aluminum AlO4, right. These are interlinked through common oxygen atoms. So, as I said TOT, a kind of structure what you get, and the T can be the aluminum, silicon, or even it can be the iron material, some gallium, germanium. So, different kind of other metal species can also be introduced into the framework of zeolite, right. So, it can give a 3-dimensional network through the long channel runs. So, right, it is a cage type structure what you get or we get from the zeolite framework based on this TOT atoms. So, the important thing is the pore structure or channel size in a zeolite. So, that is basically depends on the type of zeolite. So, different kind of zeolites are available, different types of zeolites depending upon the patents, right, name they have been named depending upon the silicon to aluminum ratio, their pore opening and the type of oxygen in the members, what you call 6 membered, 8 membered, 10 membered. So, different oxygen in number of oxygen in the ring, right, and that makes a definite kind of structure to that tetrahedral when a secondary building block forms. So, the composition wise if you see it has some cations or anions. So, M1, M2 and some 0.5, right, and the stoichiometry AlO2 some X, SiO2 some Y, and this is water Z. So, this X, Y, Z may vary depending upon the composition or initial raw materials taken, amount of these raw materials taken for the preparation during hydrothermal synthesis, right. So, this can be M1, M2, these can be the alkali or alkaline earth materials in the zeolite. So, X and Y these denote the oxide variables and Z is the number of molecules of water, right, in the zeolite, and basically it provides the protons to the when you heat it, then water removes at around 550 degree centigrade and you convert that Bronsted type acidity to Lewis acid sites. So, composition of the zeolite as I said depends on the silica to aluminum ratio into the framework and pore size of the zeolite, and depending upon these two different names of the zeolites have been given or different types of zeolites have been produced like zeolite A, zeolite X, zeolite Y, right. So, which mainly depends on silica to alumina ratio or silicon to aluminum ratio in the framework, and depending upon the water content the acidity will be developed, and cage, that is how these channels are interconnected, the primary building block and secondary building block. So, depending upon that condensation or whether it is the square from the square side or hexagonal side. So, you have a different kind of buckyball structure, that is what I was talking last time, right. So, cage openings will be different depending upon the number of oxygen atoms in the ring, right. So, one thing is the distinction from the different categories of zeolite A, X and Y is based on the geometry of the cavities, right. That is very important in terms of the opening, pore opening or channel diameter when you see the structure of a zeolite. So, different kind of channels may form, right, by the rigid framework of SiO4 and AlO4 tetrahedra, right, a prism type of structure which is a primary block basically. And tetrahedra are the smallest structural unit into which zeolite can be divided, that is what I was talking primary building block, right. So, that will depend on the T atoms which are connected to different oxygen. So, different silicon and aluminum and oxygen. structure building unit. So, we were talking on that, right, basic building block of a zeolite. So, basic building block unit, which is a primary unit, basically primary building unit, what I was talking last time, which depends on the framework, which is that this TO4, that is ALO4 or SiO4, right. So, these, say, as I said that ALO AL is not possible because of the structural instability, right, the larger size of aluminum atom, right. So, ALO Si is possible, SiO Si is possible, right, and any other metal like iron, as I said, vanadium can be added to this framework, right, that is T atoms we are saying here. So, T refers to silicon or aluminum, or it can be iron also, other metals, and which are, and depending upon the atoms which are connected to the periphery of this oxygen T, right, oxygen atoms connected to this T atoms. So, structure building unit, the basic building blocks, primary building block and secondary building blocks, what I was discussing last time for the structure building of a zeolite, that is the framework of the zeolite. As I said, it is a condensed primary blocks, right, TO4 or TOT atoms basically. So, first thing is that the tetrahedra which I was talking here, this is the a kind of structure which is developed when you have a zeolite framework. So, this zeolite framework will depend on the number of silicon to aluminum atom in their framework. So, here the related structures can be in terms of aluminum phosphate also, when the silicon is replaced by phosphorus, right. So, if you look at here that this is a kind of T atom which is aluminum or silicon, and oxygen is attached to that, right. And now, when you have the primary block or primary building, then this is a one atom of that TO4, and then this is another one, and these two are interconnected now. So, TOT what I was talking. So, this is the structure which is related to the primary or PBU unit of a zeolite, right. So, and now there will be attachments like this. So, another T will attach here, and so on, so on the structure will build, right. So, you can have different kind of structure of the primary building units also. This is what shown here, that how a primary TO4 unit can be linked to create a larger structure or a secondary building unit. So, larger structure will form from the condensation of this, right. So, you can see here. So, this is what your T atom, one T atom. So, TOT, then again TOT, TOT. So, this is what 1, 2, 3, 4, 5, 6. So, here 6 atoms are attached to this, right, a PBU unit. So, you get a structure like a hexagonal type here, right, which is, and a tetrahedral is forming, right. So, this is from the tetrahedral atoms, whatever AlO4 or SiO4, and you get a structure like this, right, 6 member. So, whatever the oxygen numbers here in the ring, and that is also the number of T atoms in the ring. So, this is what primary building, which connected to make a secondary building units in the case of zeolite, which is now in the form of buckyball. When you look at the condensation of this, so the structure, this is one unit which we have seen so far, and now they, because it is a all T atoms are interconnected now, right, and you have a cage type structure from this primary. So, this is basically hexagonal framework of the zeolite, and you can see a kind of buckyball structure which forms. So, this is how what you call a sodalite cage in the case of ZSM5 zeolites, right. So, this is a secondary building of that from the primary building TOT units, right. So, and this now this is just one, and there can be different ways of arranging these, right, and you can have different kind of this primary block, primary building structure or secondary building unit of a zeolite framework. So, this is important, that the interconnection of which produces hollow 3 dimensional structure. So, you get a 3D structure in the case of zeolite materials, right. So, 1D, 2D, 3D. So, different kind of structures can be obtained, and the entrances to the cavities of the zeolite are formed by 6, 8, 10 and 12 ring aperture, which may be now depending upon the number of oxygen. So, these are the T atoms or number of oxygen in the ring, one ring which I was talking. right. So, 6 membered ring, 8 membered ring, 10 membered and 12, right. So, this gives you the opening of that cage, right. So, small pore, medium pore or large pore zeolites, right. So, this gives you the diameter of that cage, what you have seen here in one structure of that zeolite, right. So, different frameworks of the zeolite can be obtained by these interconnecting channels of the zeolite, right. And a series of zeolites are composed, right, of polyhedra as tertiary building units. So, now primary, secondary and tertiary, and you have a definite framework of a zeolite, right, and that gives you the, because now when you are looking the structure of that, it has T atoms, right, silicon to aluminum, right. So, silica to alumina ratio will be decided, right. The pore opening, that is another, depending upon the silicon to aluminum, because I said that aluminum introduction provides the electronegativity, right, in the zeolite framework, right. So, and the silicon is there, that is also has a some kind of electronegativity, right. So, the aluminum when you introduce, it provides more and more electronegativity. So, your concentration of the acid sites will increase, right. But when you have a silicon higher, then the strength will be higher for the zeolite framework, right. So, depending upon these T atoms, the silicon or aluminum in the framework, you have the acidity or the concentration of the acid sites in the zeolite, which is the important property of the zeolite besides the pore size or shape selectivity of a zeolite, but you call a molecular sieve type zeolites also, right. So, if you look at those series of zeolites, so they are truncated octahedra sodalite or cage type structure, 24 membered rings which can be there, composed of 4 and 6 rings like that, right, in a square opening, hexagonal opening, 5 membered rings. So, different kind of structures can be obtained from these primary building units. So, sodalite cage, if you look at, it has 24 tetrahedra, right, a buckyball structure which I was talking, right. So, it has 24 tetrahedra and you call it polyhedra also, right, and generally depicted by, just as I will show you the figure of this. So, which is here basically, right. So, this is what the framework of a zeolite, right. Here the connected T atoms like this, one black one are your T atoms and the white circles are your oxygen. So, they are connected to the corners, right, and this structure framework forms, right, a 3D structure what you look at here, and this is what the I was talking connection to that bridge. So, square right here, right, this here. So, you have a 4 member here oxygen in this, right. So, whatever T atom 1, 2, 3, 4 in 1 or 4 oxygen in that, and then these are condensed, right, the connection just like if you look at a football, right, a buckyball. So, these cages are connected together and making it just like a sphere, right. So, that is what this different phases if you look at that, right, and this is these are formed because of this connection of these different structures or the primary building units of that zeolite cage. So, this is what the polygon, right, which is generated by connecting the centers of the neighboring tetrahedra with a line, right. So, that is now depending upon this connection, you have a different kind of structures or framework of the zeolite, right. So, each vertex of this polyhedron then represents a silicon or aluminum atom, that is the corner is representing now the T atom, right, silicon or aluminum, and oxygen is at the center of that, right. So, silicon or aluminum atom and midpoint of each edge is an oxygen atom. So, now when you look at one square opening, so corner is your T atom, because from those T atom another oxygen is connected and it is like a TOT what I was talking. So, all the time your structure will go like this TOT, right. So, silicon O silicon, silicon O aluminum like that, right, and then another oxygen will be there and then TOT, and then this is the primary, and then you have a cage structure by connecting those frameworks, right. So, this is what is shown here. So, these are your T atoms circled one, and this center one is your oxygen atom, right. So, you can have different kind of cage. So, this is one kind of sodalite cage which is actual and schematic is shown something like this. So, various zeolite structures now, because this is just one, right, where you have seen this membered ring, 4 oxygen in the ring, and then they are connected, right, in a sodalite cage. So, depending upon this secondary building unit, so these are different kind of secondary. So, 4 T atoms, here it is 1, 2, 3, 4, 5 T atoms, 6 T atoms, 8 T atoms. So, this can be a 1 D channel, right. Then 2 D channels are like this also, 4, 4, 6, 6, right, 8, 8, 6, 2. So, different kind of, so this is what you can see the square opening here. So, 6, 2, right. So, 2 on one side and 6 on other side, right. So, you can have a different combinations of the zeolite or zeolite framework, which will depend on your preparation condition, template, because template is the one which makes this framework of the zeolite, right, organic templates, right. So, so you can have the different kind of sodalite cage structures or zeolite framework, and the corner of the polyhedra represents the tetrahedral atom. So, all these corners are the tetrahedral atoms. So, these are T atoms basically, and oxygen is in between, right. So, once this structure formed, then secondary, as I said, that sodalite cage. So, you get a different kind of sodalite cage structure, and they have been named like that, right. But I was talking Faujas-site, Linde type, right, zeolite a sodalite cage, right. So, there are different kind of structures of the zeolite, erionite, and so on, right. So, zeolite A, zeolite X, zeolite Y, what we are talking, and these are what the depending upon that this silicon, aluminum depend the different oxygen, and or basically in terms of the raw material which has been taken, right, the concentration of the silica species, concentration of the aluminum species, then pH and then the decisive factor, amount of water which is showing the value of Y in the zeolite, right, then temperature which will give you a kind of nucleation, crystallite formation, right, time where the hydrothermal synthesis, because it is a autogeneous pressure synthesis, right, at high pressure under autogeneous. So, it generates the autogeneous pressure because of the presence of water, right. So, you have and that time, right. So, reaction time or aging time. So, you have the different kind of phase or crystallization that you check during the time course of the formation or synthesis, right. So, this is just a one kind of sodalite cage which we have already discussed. Now, how does it form from the primary building, then secondary building unit, and then tertiary, right, or which is nothing but the secondary building which forms from the condensation of the primary building. So, this is one sodalite cage structure which I have seen in details, right, with the square opening and 4 T atoms in the group, right. So, one cage, and then there can be the condensation of this tertiary building block. So, 1, 2, 3, 4 like that, and so on, a buckyball structures, and these are interconnected like this, right. So, 1, 2, 2. So, you can see that several footballs placed in one cubic structure inside inside a box, right. So, that will be a structure of that, what the sodalite cage or a zeolite structure, right. So, that is what the 3D type of structure what you get, or a framework which forms because of the opening or because of the gaps between them, right. So, this is what the one sodalite, and there is again when they are connected in a different fashion, here it is in this fashion, but here the this is something different if you look at here the openings of that. So, connection is different in the polyhedra form, right, the attachment of these the structures which are connected, right. So, hexagonal or 5 membered pentagonal like that. So, same thing here. So, a different pore size, right, you will have different opening with the there's the silicon to aluminum ratio may be same, right, but the opening will be different, right, because it depends on how they are not how they are connected, that how the structure is connected, right, and a different one where large numbers are number of cages are connected together, and number of those silicon to aluminum or T atoms in the framework. So, we categorize them or we just name them accordingly. So, the one structure which is one type and second type here. So, those are zeolite X, right. This is your zeolite Y with different opening if you look at here, right. So, it has different ring structure here compared to this one, right. So, size is different, right. So, and this is another one. So, you can see the building block. So, this is different, just a 1, 2 like that, and they are interconnected, right. So, ZSM5 a pentacell structure here, right, and this is the actual ZSM5 channels, pore channels, right, in a 3D array. So, that is a 10 ring 3D GSM-5. So, as I said that it depends on the projections of this primary building block or framework, right, along principal crystallographic direction of 8 zeolite structures which have been shown here, right. So, basically these all depends on the primary building blocks which I have shown you in the earlier slides like this, right, and then their orientation, that is the structure which is how does it project on that one primary block and how does it project, that is the secondary block, and then the multiple which have formed, right, the tertiary blocks. So, depending upon the projections of these principal crystallographic directions, you can have 8 zeolite structures which contain just 5 rings units. So, one GSM-5 I am talking, right, which has a pentacell structure suppose, but there also you can have different type, right. So, this is mordenite, just if you look at the here if you read here, that directions of 8 zeolite structure that contain 5 ring units, right. The structure is drawn as straight lines connected adjacent T atoms, and in each case these are based on reported crystal structure, right. The unit cell obtained are indicated by the dashed line. So, this is one unit cell of a zeolite. Here it is the unit cell of a zeolite like this. In this case it is a something different like this. So, it means depending upon the arrangement or orientation of that crystallographic plane, right, the plane orientation, just so different type of zeolite openings may be arrived, right. So, a different structure of the zeolite may be seen in terms of the pore size. So, same silicon to aluminum ratio, same number of T atoms, but the pore openings will be different. So, we categorize them depending upon small pore zeolite, medium pore zeolite and large pore zeolite, right, with the same silicon to aluminum ratio, because as I said that zeolites are mesoporous material or the microporous material, right. And then the pore structure of the zeolite, because they have the importance in terms of the shape selectivity, they are very useful for the reactions where the selectivity may be an issue, right, especially in the most of the hydrocarbon industry or petrochemical industry where selectivity has an issue, right. One desired product is required in large amount compared to the rest. So, suppose the coke is forming in large amount. So, you take a catalyst in such a way where the coke, which may be a polycondense aromatization reaction, right, the aromatics are there and they condensed and form a aromatic bridge, and which is a polycondense aromatic hydrocarbon. So, if the pore openings or the kinetic diameter of the pore, this poison precursor or sulfur or whatever the coke precursor aromatics, if the kinetic diameter of these molecule is smaller than the pore diameter, then they will not go inside, they will not form the coke type of hydrocarbon, right, or the sulfur molecules if they are there. So, you can have a kind of shape selectivity from this zeolite, and especially when you look at a green catalysis nowadays, right, then you are looking in terms of atom efficiency, right, or E efficiency. So, the product, when the multiple product may form from one of the raw material, then this becomes very important, just like methane conversion if you look at, or Fischer-Tropsch reaction where the product may be methane or wax also, and the interest is towards the gasoline or diesel range of hydrocarbon or methanol, that is a selective narrower range of hydrocarbon. Then these kind of catalysts where you have a narrower pore size or a selected pore size distribution, then this may be a better option as a support or as a catalytic material. So, depending upon these structures, we have different kind of zeolites here, right. So, and these are named as per the International Zeolite Association. So, the structure of the zeolite has nothing to say about mordenite if I say, or beta zeolite, right, beta B zeolite or MFI zeolite, mobile 5, right, this ferrite type zeolite, TON type zeolite. So, these are just the IZA named, right, for a given kind of zeolite. But here what I want to say that depending upon the principal crystallographic direction, you can have the how this principal crystallographic orientation of one primary building and the secondary to form a multiple, right, or a polyhedron, that depends on the type of the that is the orientation depends to give a given kind of pore opening in a zeolite, and accordingly these have been numbered. So, the name, that is nomenclature for a zeolite, as I discussed last time also, that is very important, right. So, a 3 letter code system has been developed for the zeolite. So, to identify a zeolite or a type of zeolite, a 3 letter code system has been identified. That is what as I said, that IZA is one, which just designates a zeolite in terms of their pore size distribution, silicon to aluminum ratio, or the opening, what are the cage opening, what I said earlier. So, generally they have given a 3 letter code, right, and which is related to a specific structure types and independent of their actual chemical composition. So, whatever the M or M1 and M2, which I talked in terms of the structure, SiO2 X or right water Y, AlO2 Z, something like that, right. So, these structures have nothing to do with that composition or name of the zeolite, right. Composition has nothing to do, these are some patented names, right, and the only thing that once these numbers have been identified and one can compare the property of the prepared zeolite with those standards, right. So, these are kind of benchmarks which have been tested for the certain reactions, and their pore size, pore structure, opening, silicon to aluminum ratio, these are well defined, right. So, this is one important nomenclature for the zeolite material. So, just LTA, suppose if you say, so LTA is used for zeolite A and is derived from the name Linde type A, right. So, Linde again a company, right, based on that the just like I was talking Virginia one, right, or zeolite, Suconi, Mobile, Jedisum, right. So, these are name numbers, right, to identify the zeolite. So, here the 139 structure types of zeolites are available, and even more than that may be available. So, the 3 letter codes what I said, LTA refers to the Linde type A, Faugasite represented by FAU, MFI which is a kind of Mobile 5, BEA refers to beta zeolite. So, different kind of zeolites are available in that, say like LTA zeolite A, zeolite X and Y, they are Faugasite type category, Jedisum 5 well known category of the zeolite, right. So, Mobile, sometime the Mobile Suconi, right. So, that is again the name which has been given by the Mobile group, and beta zeolite which is zeolite beta, that is the name, right. So, like that you have, it can be silica, aluminum, oxygen, it can be a germanium in the framework, and it can be a gallium phosphate oxygen, right. Again, so different kind of zeolites are available in whether in LTA or Jedisum 5 or MFI group or beta type or FAU type, right. So, silica aluminum ratio may vary, pore opening may vary, structure may vary. So, as I said that molecular sieves, zeolites are also a kind of molecular sieve, right. So, the name says the molecular sieve where just the molecules are being separated depending upon the size, right, the size of molecule and the pore size. So, one can separate the larger molecule from the smaller, just like in a membrane, right. So, but there are certain differences, or if you just look at the properties wise, there is a difference between zeolite and the molecular sieve, right. So, zeolites are class of material which possess selective adsorption property. So, they have very good adsorption property, because as I said they are sieve selective, or sieving action is very important in terms of the pore diameter. So, diffusion may be a governing process here, right. So, selective adsorption property, and that is based on the molecular size, right. Whereas, if you look at in the zeolite, right, in contrast to the molecular sieve, they are molecular sieves containing aluminosilicates as skeletal composition, right. So, they have the 3D structures, or they contain the aluminum, silicon, right, and in some cage type of structure, right. So, the one thing is that here it may not be a uniform, right, the crystallinity may not be an important issue in the case of molecular sieve, but in zeolite the crystallinity is one of the important issue, right. So, a definite type of zeolites when we name that should have a definite crystallographic property and which you can differentiate from the X-ray, right, or XRD analysis one can identify the phases formed, right. They may be crystalline, they may be non-crystalline or partially pericrystalline, right, if you look at molecular sieve, but zeolites are most of the time they are crystalline in nature and that is their property, right. The definite shape and the phase is important property of the zeolite and they have a definite crystal structure, right. So, both are porous in nature. So, molecular sieves are porous, they can be, but in the larger pore size also, right. A wide pore size distribution may be available in the molecular sieve, but in zeolite these are basically microporous or mesoporous material. So, most of the time we talk microporous, right. So, that is important when you look at a catalytic reaction activity, right. Then framework cations, right, and coordination, this is a variable, right. In the case of zeolite material, you know that it is a tetrahedron, right, that is a primary building unit in the case of zeolite, but in the case of molecular sieves it is not well defined, right. So, it is just like a 1D channel with some cations, right, in the framework, right. Then variable framework chart, because cations, right, they may change and you can change the cations concentration, type of cations. So, these are variable in the case of molecular sieve, but in the case of zeolite because it is anionic, because silicon, aluminum they are connected in a definite array, right. So, a kind of electronegativity, right, that is what you get in the framework of the zeolite. So, they are anionic framework charge, right. Just for example, if you look at in the case of molecular sieve, the crystalline material are SAPO, silico-aluminophosphate type zeolites, right, and non-crystalline these are carbon type of materials, right. Carbon nanotube can be one type of that, right, porous carbon materials, microporous, mesoporous carbon materials, right, and pericrystalline materials like MS41 again a code name, pillared clays, right, silicates, clays are silicate types, lamellar structures. So, these can be a molecular sieve type of zeolites, right, or molecular sieves I should say rather saying a zeolite type, right. Whereas, in the case of zeolite because they are definite in framework, so ZSM 5, ZSM 12. So, most of the zeolites coney mobile that is what the type of zeolites, right, available for commercial use. So, characteristic wise, because zeolites are now very specific, right, in their action. So, the properties of the zeolites are very important. Why zeolites are important? Because they have high surface area, because these are microporous, mesoporous material, right, smaller pores, but large number of pores are available. So, their surface area is high, internal surface area and external surface area of the zeolites. If you have a nano kind of zeolite material nowadays, again these kind of materials may be synthesized, right, nano materials, nano zeolite, the external area may also be high, right. So, that is again an important issue and these kind of zeolites may be useful for some specific catalytic reaction also, right. So, they have very high surface area, uniform micropore size. So, unlike in your other commercial catalysts like alumina, right, or silica, ceria, zirconia, they may have a wider pore size distribution, right. So, depending upon your sintering condition and calcination what you have done, calcination condition during calcination the sintering may take place or at high temperature solid solid reaction. So, their pore size may vary in wide range, but in the case of zeolites, right, the nucleates which forms and the crystals which develop during your hydrothermal synthesis, that is very important, and the framework depending upon the framework of that zeolite, their pore openings are in a narrower size range, right, because it is a kind of definite reaction or it when you talk a hydrothermal reaction basically at high temperature and the sufficient pressure, right, and you have the controlled pH, some organic templating agents, water, and there the nucleation takes place. So, crystal forms and these crystals when they grow they have a definite kind of structure. So, preparation of zeolite is entirely different compared to non-zeolite materials, right. So, there here the phase and cage opening is very important. So, they have a uniform and micropore size or micro mesopore type of size, right. Hydrothermal stability, because they are prepared under hydrothermal synthesis. So, they are thermally stable under certain conditions, right. The only thing that the depending upon the type of zeolite, and as I said nano synthesized zeolite material, they may not be stable at very high temperature, right. So, roughly up to 550 degree centigrade or 600 degree centigrade, these kind of zeolites are thermally stable, right. They have sufficient acidity, defined acidity, right. So, as I said, the acidity can be determined by IR adsorption, right, IR spectroscopy. So, pyridine is used as a reference, because pyridine is a base. So, the molecules of the pyridine adsorbed, right, on the catalyst, and then it is measured, right, adsorption is measured, and then you can have the idea about their the Lewis type acidity and Brunstedt type acidity. So, in the case of zeolite, as I said, that silicon to aluminum ratio is very controlled and important. So, that decides the acidity also of the zeolite, right, H positive ions which are there in the framework, and that provide the Brunstedt type of acidity. So, in the case of zeolite, these are well defined, right, it is a well defined structure of a zeolite. So, the acidity is important and it is defined, right, and they have ability to accommodate active metal species. So, you can exchange that, right, ammonia exchange, that word gallium exchange, HZSM5 which I was talking, by replacing the protons, right, and you can add sodium there, calcium there, ammonia there, right. So, all kind of gallium. So, these kind of metals can be added to the zeolite framework by ion exchange method or by incipient wetness method also, right. So, you can have mordenite, molybdenum, and MO HZSM5 molybdenum can be associated to the framework, right, or different copper, gallium, right, which are good for some catalytic reaction. So, size constraints, if you look at, or molecular sieving, because we are talking about the pore opening is also important in the case of zeolite, right. The catalytic activity is not only because of this silicon to aluminum ratio which is providing the acidity, but also the pore opening, because that controls the mass transfer or diffusion in a pore, right. So, your that when you have the certain kind, of course, the diffusion may be dominating if your molecular size are larger, right, relatively larger, or the conditions are not severe. So, that is one issue in the case of zeolite material, right. The reaction may be a diffusion controlled also if you are not properly designed your catalyst, right. So, one has to check that also, right. So, I just said that it has rigid skeletal system, right, all zeolites, right, they have a definite framework and very rigid skeletal system. So, because of that, the zeolite window has intact window size, right. So, a definite pore opening, what I was saying, because of the a buckyball structure where you can have 6 membered ring, 4 membered, right, 4 4 or 6 6 2D channels. So, they have a definite kind of opening, right, and depending upon that, the molecules, right, having size larger than this window dimension, they often experience constraints in accessing the intrinsic side. They cannot reach, right. So, it will depend on the kinetic diameter of the molecule versus the pore diameter or pore opening. So, I should not say pore diameter in the case of zeolite, because it has something like A into B, right. The channel diameter, it may have a different size, right. So, A into B 5.7 times whatever into the 5.4 or whatever, right, cage structure which may have different openings on x and y axis. So, that is one thing. So, that is a kind of sieving action. So, how many molecule can diffuse inside under a given condition, temperature, pressure, right, where the diffusion coefficient is to be calculated for that given molecule in a mixture, and then you can calculate that diffusion, right, how many molecules are diffused, and then accordingly you have to calculate, right. So, that is one sieving, that is the restriction, right. So, this prevents the undesired large molecule to enter the network. So, that is good in one way if you have the multiple reactant species, and some of the reactant, some of the species rather which are present in the reactant are impurities, like sulfur molecules, right. When you have hydrodesulfurization reaction and the sulfur or larger molecular weight sulfur, what I am talking, a thiophene, dibenzothiophenone, right, which are large sulfur molecule. So, these can be separated, or sulfur removal can be done by using a selected type of zeolite material, just by adsorption, right. it can act as a sieving material. So, in a definite kind of zeolite material, so I can have right the feedstock from which the feed, that is the naphtha or larger molecular weight compound can be retained, they cannot pass through that zeolite material, but smaller can pass through that, right. So, your cleaning or purification type unit, right, and right that can be one way, that right. So, because they are shape selective, or I can have the other way also, like just say polymer or some kind of polycondensation, as I said, aromatics are forming, and aromatics are forming because of the say some coke is forming because of some aromatics which is present in the feed, right, larger molecular weight aromatic hydrocarbon. So, they may not go along with the hydrocarbon feed mixture. So, they may be stopped. So, zeolite will not allow them to pass, or this can be a transition also, that is during the reaction some kind of intermediate forms, right, which may prone to coke formation, right. So, that is what I said, that suppose you have taken methane molecule, methane can diffuse inside a zeolite. So, it will transform into a larger molecule, it will form some kind of say olefin, olefin can react further, right, they dehydrogenate or they oligomerize, right. So, they can form a larger molecule, but when your pore openings are limited, then it cannot form a very large molecule, it can form only selected range of hydrocarbons, suppose C5, C6, C10, depending upon the kinetic diameter of those molecule, and that can easily come out in a given time. Diffusion length is also important in that way, right. So, that your further larger molecular weight compounds can be stopped because the pore length is small, right. So, your diffusion resistance will be low in that case, or simultaneously it will not allow to form a very large molecule because the diameter of the zeolite pore is smaller, right. So, this kind of sieving action can be molecular sieve is very important in the case of shape selective zeolites, when you look at the reaction where you do not want to have the undesired reactions or undesired product in the reaction, right. So, that in that way the zeolites are shape selective. So, product selectivity may be important, or sometimes it can sieve the reactant which are undesired reactant raw materials, that can be selected as a shape selective, right. So, depending upon this shape selectivity, and these are classified into three main subdivisions, that is what I already discussed, that the. So, I should just talk that first, shape selectivity of the zeolite, which is related to the this one, right, reactant shape selectivity. So, reactant shape selectivity is something where you have just look, if you look at here, the molecules are oriented like this. So, they can pass through that, right, but a reactant species which is something like that, it has the difficulty to pass through the pore, right, because it is something like an isomer or it is a kind of ring compound, right. So, that may not pass, but if it is along the compound is just like a straight chain paraffin hydrocarbon, right. This is something like your suppose butane or heptane, right. So, that can pass through the zeolite framework, right, but this kind of molecules which may be aromatics, right, or some isobutane, that may not go because the structure has branches now. So, that has different kinetic diameter, right. So, that is a reactant shape selectivity. Second is the transition shape selectivity, which I was discussing, right. So, that is referring to curbing of intermediate compounds that formed in the framework of the zeolite, whose size is larger than the skeleton size. So, that is what I was saying, polycondensed aromatic hydrocarbon, which is a coke precursor, right. So, these may not go into the framework of the zeolite, or it may not form inside the zeolite because of the pore size. So, due to the restricted pore size, the product diffusing through these materials, right, they experience a constraints, and so product form is also selective in nature, right. You do not get the undesired large molecular weight compound because of this transition shape selectivity nature of the zeolite, right. So, but sometimes when the bulky products accumulate over a position of the zeolite, that blocks the accessibility of virgin molecule, right, resulting into coking or deactivation of the catalyst. So, these are some limitations that sometimes the zeolite pores you see in the case of catalytic cracking, FCC, right, fluid catalytic cracking, because the hydrocarbon which gives you a large molecular weight hydrocarbon, when it cracks, right, it forms some kind of say gasoline range of hydrocarbon, right, C5 to C10, right. with some isoparaffin, more isoparaffin, these are desired, or some kind of diesel also you can get, right. But sometimes beside these there may be, because it is not just a single reaction, there are several multiple reactions, secondary reactions which do take place during that time, right. And when this happens, the coke may be also one of that, right, and that blocks the deactivates the catalyst, right. So, in fluid catalytic cracking you need a continuous regeneration of the catalyst, right, and that is what the fundamentals of the design of the fluid catalytic reactor, and you need a regenerator also side by side, right, and there the generally these zeolites or stable zeolite catalysts are used. So, this is what the product selectivity I was talking, that there can be a one ring compound which opens like this and forms this, right. So, when you have a favorable reaction, you want a favorable reaction, this should form, that is just like say if you look at the xylene separation, if I just say ortho, meta, para, all kind of xylene may form, right, when you have the isomerization of xylene, right. So, ortho, meta, para, but a definite meta is say undesired, right, para xylene may be desired one. So, you can have the some kind of isomerization like this, right, but this may be unfavorably meta xylene, right. So, this is what the safe selective product formation. So, if you have a proper tuning of the zeolite pore size, so it has nothing to do with the acidity of the zeolite, that is different, that we have to look at in a different aspect, that if cracking is desired what kind of acidity is required, but right now we are talking just based on the molecular sieve, that is the type of molecular sieving action with some acidity is there in the catalyst, but right now we are just talking based on the shape and size of the molecule. So, it means these kind of reactions or adsorption, they are related to the kinetic diameter of the molecule versus the pore diameter or channel opening of the zeolite. So, one has to look at the channel size of different zeolites A, B, C, D like that whatever they are, and the reactant species, their kinetic diameter under the given condition, what molecules can diffuse or cannot diffuse, and then one can have the selection of a particular kind of molecular sieve zeolite for a given reaction. So, let me go back now again. So, we were talking now the structures of the zeolite, and before that the acidity of the zeolite. So, we have already said about that two type of acidity may be possible in zeolite. One is known as Bronsted acid side, which is because of this proton, right, H plus, right. So, terminal cyanol group and contains the H, right, and when you heat it, it goes to the Lewis acid side, which are basically because of these, right, presence of these in the framework of the zeolite, right. So, stronger acid site and weaker acid site. So, protonated zeolites or these are ability to exchange a proton or ability to donate an electron, right. So, depending upon that the Bronsted acids or Lewis acidity is defined, right, correct. So, the Bronsted side means it can donate a proton, it has proton, right. Lewis acid side means it has ability to accept an electron, right. This is what shown here. In the case of zeolite, when you heat it to a 550 degree centigrade temperature, then this Bronsted side which is shown here H, right, proton, that converts to a Lewis acid side like this, some kind of negativity. So, it can donate this electron here and the water gets separated. So, this is your water, right. So, this is what the shown here in the transformation of this to this, right. So, protonated zeolites, they have the acidic property as I discussed before also, and the proton which balance the negative charge of the zeolite framework are not strongly bound to the framework. So, they are mobile in one way, right. So, they are not strongly bound to the framework. So, they are able to move within the pores and react with molecules which penetrate into the zeolite pore system, right. So, because they are mobile in the framework of the zeolite. So, when the reactant species, just like a cracking reaction, right, you need a kind of protons there, right. So, it forms, because the cracking is basically based on the carbonium ion mechanism, right. So, methane carbon, the cracking of say heptane, the even pentane, right, and earlier it was naphtha cracking, right, the pyrolysis naphtha basically for olefin, but cracking of naphtha is basically for the gasoline range of hydrocarbons. So, FCC cracking which you see now for atmospheric gas oil or vacuum gas oil, right, or residue VR. So, that is based on, that is zeolite based catalysts are used, because they have the strong H positive ions there, right. So, this is based on, cracking reaction is mainly based on the carbonium ion mechanism, right, and then the secondary reactions take place and you get the kind of gasoline range of hydrocarbon, which is known as FCC gasoline, right. So, this is important in the case of Bronsted type of acidity, right. So, a protonated zeolite thus can act as a Bronsted acid. Structure wise, if you look at that, we have talked so many times now. So, the structure of zeolite, which is A type zeolite now, right, Linde A. So, it is a narrow pore zeolite, right, and which is formed by linking the square faces of the polyhedral via intermediate cubic unit. So, this is the same thing what I talked before, that the primary building, then secondary building, and then the tertiary, right. So, in A type you have square faces of the polyhedral, which is connected by intermediate cubic units. So, something like what is shown here. This is 8 membered ring here, right, and zeolite A type structure. So, this is one, if you look at these kind of connections here, and these are, this is the bridging between two buckyball structures. So, one sodalite cage, another sodalite cage, and they are interconnected, right. So, you have the channels which are something like this, based on this connection of roughly 0.41 nanometer. So, same on both sides, right. So, 8 membered ring, but bridging is from the square side here, right. So, the framework structure of zeolite A with alpha cage. So, square faces of the polyhedrals are interconnected. That is what I said, that several footballs are placed. So, which face is now, right, with framework of that crystal is attached or oriented. So, that will give you a kind of opening of the pore, right. So, the cavity formed by linking 8 truncated octahedra, that is known as the cage, right, alpha cage, beta cage, what I was talking, right. Different kind of cage structures or sodalite cage structures can be obtained from this, right. In the case of wide pore zeolite, say zeolite Y. So, narrow pore zeolite, it means, because you know that narrow pore zeolite means it will have 4 number of rings, 6 numbered rings, like that, right. And again in hexagonal to hexagonal or squares are edged, right, faced, what I said, projection of that, right. So, in case of wide pore zeolite, that is larger diameter zeolite, which is just for example, a zeolite Y, phosphite type, right. So, phosphite is a large pore zeolite, Linde A, that is type A zeolite, is a narrower pore size zeolite, Gypsum 5 is a kind of mesopore zeolite, right. So, the wide pore zeolite Y, which is phosphite, so that is formed when the truncated octahedra are linked together by a hexagonal prism, right. So, small pore by square, and these are connected by a linked together by a hexagonal prism, and this resulting cavity is larger than the cage of zeolite A. So, you can see here, right. So, this is now the one hexagonal, this one. So, these are connected, all these hexagonal, right, octave, the framework is connected in this way, whereas see both are similar buckyball structure, right. So, but the connection instead of here, it is now from this side, this is one, right, which is shown now projection here, and the same structure is here, if you look at it here, this side. So, it means the orientation of that, right, framework, one cage sodalite, and there are several sodalite cages are attached. So, they have some square, some hexagonal frame. So, which is connected to that another cage, right, and making a structure. So, you can see here that this is 0.41 nanometer, but here it is 0.74 nanometer, and the number of oxygen now in the ring is 12 rings, right. So, this is a Y type zeolite, which is based on the hexagonal prism, right. So, representative of the medium pore zeolites, these are known as pentacell. So, structure wise, which I have shown before also, right. So, pentacell zeolite and belong to the silicon rich zeolites, Gypsum 5. So, in the case of Gypsum 5, the silica to aluminum ratio goes from say 10 to 500, high silica to silicon to aluminum ratio, right. So, in contrast to the structure of zeolite A and faugasite, which we have seen earlier, the polyhedra are composed of 5 rings as a secondary building unit. So, in A it was 4, right, in the secondary building, right, the different building blocks which I have shown before. So, in the case of zeolite A it was 4, right. In the case of faugasite it was hexagonal, right, prism, which you have seen in this case, this, right, this is 4, this is 6. In the case of zeolite it is 5. So, that is why they are known as pentacell, right, zeolites. So, they have 5 rings as a secondary building unit SBU, right, and that is why they are mesopore in nature. So, it means the 0.41 I told as a microporous, right, 0.71 nanometer is a kind of a macropores, right, or larger pore, not the macropore, but these are smaller, that is in between these two, right. But in the case of zeolite or faugasite we do not have the macropores basically, right, because they are already in a framework of the zeolite, not the pore space between the particles, right. So, that is what the zeolites, when we say J 5, these are a mesoporous type of metal, right. So, which has the between say 20 angstrom to say 50 or 100 angstrom, something like that, right. So, these so called 5-1 units, right, and are structurally analogous to methyl cyclopentane. So, just like if you look at methyl cyclopentane, the structure of the J 5 is something like similar to that here, right. So, roughly 0.56 nanometer, this is the opening, and these are 10 rings in this, right, oxygen rings, but the framework is from the pentacell structure, which is shown here if you look at here, right. This is one, right, like this. So, all these pentacells have made this one cage, and this is what referring to this, right. So, this is your SBU basically, right, secondary building unit, where all these centers will have T atoms here, all these, right. Corner will have these corners have T atoms, centers has oxygen atom, right, and then these are connected with that pentacell, and this is making one 10 membered ring, one 10 ring. So, it can be 10, 8, 12 like that in the case of zeolite itself, right. Different kind of zeolites are available. So, this is what the channels of that zeolite, right. So, linking of the resulting chain, that gives a 2D pore structure, right, in which the linear or zigzag channels are intersected by perpendicular linear channels, right. So, there can be a different kind of structure of J 5, which is here shown in terms of the pore opening. So, J 5 is something like a pentacell zeolite with this kind of channel structure, but silicon to aluminum ratio may be varying, right, it can be different. So, I will stop here and I will continue it next time. Thank you.